Before we launch into our study of time-dependent phenomena, we're going to have a quick look at Ohm's law in a recast form, and there are reasons to do this. You'll see that we need this machinery when we come to study time-dependent phenomena. So this first segment, or this lecture is really about recasting Ohm's law in a new and useful form. So you'll remember Ohm's law from your first year studies or your high school studies. We might have a battery with potential V and resistance R, and the current flowing through the resistor is given by I is equal to V divided by R. So this is Ohm's law in a familiar form. Now the form of Ohm's law we're going to develop and study is the following. It's completely equivalent, but it's the current density J is equal to sigma E. All right, so the reason that this is a useful form to write Ohm's law is that it allows us to study bulk materials, all right, not just materials that are one-dimensional wires and one-dimensional resistors. If we have three-dimensional flows of current and three-dimensional electric fields, we now have a relationship between J and E. Now, I'd like to remind you that the Ohm's law it's not a law, all right? Some materials obey Ohm's law to a reasonable approximation to make it a useful rule to describe, but actually there are many materials that just don't obey Ohm's law at all. And we won't be too concerned with those in this course. Right, so what I'd like to do is just establish the relationship between this form of Ohm's law and that form of Ohm's law, so that you understand that the two are indeed actually the same. Imagine we had a material, I'm going to draw it in the following way, that had conductivity sigma. I'm going to give this face area A, I'm going to give this length L, and we're going to have an electric field which is constant. And furthermore, the electric field is going to be given by, let's say the magnitude of the electric field is going to be the potential difference, which I'm going to call V, divided by L. So there's a potential difference between this end, and that might be being supplied by a battery, for example. So V is that potential difference. So I've got this new form of Ohm's law, J is equal to sigma E, and what I'm going to do is I'm going to integrate both sides of this equation across this surface area here, and then I'm going to rewrite the electric field as V divided by L. So let's do all that. Okay, so here then is that calculation. I've integrated J dot dA over this face, and I've made a bunch of assumptions in this problem. Of course, the integral of J dot dA is the current. It's the total current flowing through this thing, so there it is, I. And now we integrate the right-hand side, which is E dot sigma dA. That I should write that as a vector, so let's do that. Okay, and I'm going to assume that E, the electric field, is constant, and that it's parallel to dA, and sigma is a constant, so all of this just becomes sigma A times V on L, and I've rewritten E as V divided by length, as I said I would over here. And if we put all that together, we get the current is equal to sigma A on L times V, and this is completely equivalent to okay, this is completely equivalent to I is equal to 1 on R times V. So in other words, R now is equal to sigma A on L. This is, or pardon me, 1 on R. 1 on R is sigma A on L. So as the conductivity increases, the resistance of the material decreases. That makes sense. As the area increases, the resistance goes down, and as the length increases, the resistance goes up. So this is our new form of Ohm's law, and we'll find this to be fairly useful as we progress through our study of dynamics, so time-dependent phenomena.